Okay, so the final draft for the game engine portfolio thing. It's a 2.5D platformer just like I did last year, but I wanted to revisit and basically prove how my skills have improved. So what I did first was I blocked out the level using this one kind of rock and the interactive cube, but reskinned to the rock texture as the playset mats for the lasers. We've got wall jumping, a harming laser. You can drag the cube around for a more puzzly aesthetic, and then we've also got this elevator here. So I'll show you a quick playthrough of it. You can see there is that one little bug. But for some reason it's catching on solid flat ground. I couldn't figure it out for the life of me. You go over here, the elevator goes up. When we come off of the elevator, it goes back down. And there's also another bug on this cube right here. For some reason it rotates the player out of line, so it can't touch the win state. I'll show you what the win state looks like right here. It's just that. And the death screen is the same thing but red, and it says you died. But I will show that to you now. So let's start with the HUDs. As you can see, the very basic. This was just a image. Lower the opacity, make it red with the you died text. The you win is the same. Lower the opacity, make it green with text saying you win. And then you've got the main HUD, which has the E to interact, which is hidden most of the time unless you're within the collision box of the interactive pieces, like the cubes that you can drag and the elevator right here. And you've got your health bar and your energy bar. If we go to the percent, you can see it's different colors underneath on each of them, so it's nice and readable. But the normal game mode, which is when when you begin playing the game, it adds the HUD that you just saw to the viewport. And then we get into the ball. This was an asset I found on the web with a sphere capsule component, a spring arm on the camera, which is huge, which is connected to the ball. So when the ball moves, the spring arm that has the camera on it will also move. Then we go into the event graph, and because I wanted to do everything from scratch, it was quite annoying. What I did was I went and sourced out a material on the internet that had these parameters right here. I wanted to find a material that had these because it would mean that the ball can actually have interactive bits and pieces within it, like in this project. As you see, when you load in, it boots up to a green color. As it gets damaged, it changes color to a more reddish color until it's fully red when it's dead. And that would be what happens in this. So you've got the custom event of changing the ball's material color. Take the parameter name, which is either power or is active, which is up here. Set the scalar parameter value to be the ball material instance, which is right here. It's a material instance calling to this material, and the value being the value. Then we want to set that material to the ball again. So that's calling to this. So we want to set the material instance to be the ball's material. And then we want to change the color of the ball right here. So we've got the change ball material color, which is this custom event. Got a delay and change it again. So right at the beginning, it will change the ball's material color, the parameter being is active, to 0. So if we go back to the thing here, you've got the is active here, which can change the colors. I'm not going to pretend like I know how it works because I don't. I just know that it does. And then change the ball material color to a value of 1 after a delay of 0.5 seconds. And we've got a timeline here, which is just the curve float of 0 to 1. So it's this right here over the course of 1 second. And then updating, it changed the ball material color each time this happens, with the value being the alpha, the power being B, and the A being 0. So you've got the 0 being completely red and 1 being the completely green. And it will go through, make sure it checks, and the lerp make sure that it's a smooth transition between the two. And once this is finished, enable the input. So as you can see, like right at the beginning here, if I try to move around while it's booting up, it doesn't work. But if I move around once it's finished going green, it does work. That's what this is doing here. So right at the beginning, we've got the disabling the input while it's booting up, and then enabling it once it's finished booting up. Then we've got the enable disable input here, which is just if it is enabled, make sure it stays enabled. If it isn't enabled, make sure it stays disabled. Just that sort of thing. Then we go to the movement update. Because all of this was done off a blank project, I had to put in the movement manually instead of it already being there. Puzzle mode was something that I was going to implement, but due to time constraints, I just made the puzzle mode active, like make sure that it's active. So if puzzle mode is inactive, in this case, set the move direction, which is a thing down here. Make the vector get move right, which is from the character movement. And then same for the false. So we get move right, times it with the actor's forward vector, and set that as move direction. This is what's actually moving the character. This, as far as I'm aware, is doing nothing. And then we put these both together and put it in an add movement input and make sure that it's normalized, otherwise it will kind of mess up. And then because it's a ball, we want it to rotate and not just be static. That's called to up here as well as the movement update. So if we unplug the rotate ball, plug this straight into there, unplug this, put this into here. So if we take out the rotate ball, you'll see it's just this. It doesn't look very immersive. So we needed to add in some way to rotate the ball in a nice, like, fluid way, which is where this comes in. So we've got the flat velocity. So we want to set the velocity to be the velocity, strangely enough, of itself, but we don't want it to have any velocity on the z-axis because, well, if you're rolling around, you don't want it to really rotate in a direction that you're not going to be able to go. Then we set that velocity, make sure that we set a vector length, take out the vector here and get the vector length and set that as the current speed. And then what we want to make sure is, as long as the current speed is not equal to 0, we want to make sure that it isn't equal to 0, otherwise you're going to be rotating while standing still, and that just doesn't make any sense. So if it is greater than 0, then we've got this massive amount of math that just took way too long to figure out. It was just a lot of, okay, the flat velocity that we've already got that was set over here, make sure that we get the vector length from that and divide it with the ball's rotation rate, which we put to 0.75. If we make it like 1, for example, it will just make it rotate a little bit quicker. And multiply that by pi. For some reason, pi was the only thing that made it remotely worth actually a remotely realistic rotation speed. And then we want to multiply that by the delta seconds of the world, and then add that with the rotation amount and set that as the rotation amount. And then we want to set it as the world's rotation, with the ball being the target, which is our mesh. And we want to make a rotator from axis and angle being the right vector. So we want to get the flat velocity, which we set over here, make a rotation from the x-axis and get the right vector and make that into a rotator, with the angle being the rotation amount, which we set right here, and the axis being the axis from the flat velocity, and return that to the world's rotation. When I was first messing with this, it did have a bug where for some reason it was also rotating the camera, and I haven't been able to replicate it since, otherwise I would show you it. I don't know how I fixed it. All I did was I went in and I moved one node. I just disconnected it and reconnected it, compiled and saved, and for some reason it worked. So we also wanted to get the input action of jumping, which was incredibly simple to get the basic jumping because UDK has an inbuilt jump. It's pretty much that simple, but the wall jumping was something else. So we wanted to make sure that the player was falling, because if they are falling, then, you know, we don't want them to infinitely jump. Like if we just switch these around real quick, I could just show you what it does if that is the case. Actually, I don't think it would let you jump at all if you're, yeah, but if I fall off here, never mind, it didn't work. So, yeah, that does that. I thought it would just allow you to infinitely jump. Never mind, I was wrong. Either way, the wall jumping mechanic that you saw in my little demonstration was all done using a line trace. But the start of the line trace, we get the actor's location and we subtract that from the scaled capsule radius plus 10 and the actor's forward vector. So if the character is going this way, we want to make sure that it's equating for the speed and the capsule size at plus 10. Then we multiply those together and subtract it from the actor's current location, and that will give it a small little, a tiny little line trace instead of one that goes the entire map. Otherwise you'll be jumping off walls that you can't even see. So if we jump along here, you can see how small the line trace actually is, because the start place is the actor's location subtracted from this, and the end location is all of this, but plus the actor's location. And then from there, want to branch, the return value being if it is actually hit something, and we want to launch the character after that. But the launch velocity on the X has to be the actor's location, split the struct of the vector, return value X, subtracted by the location X of whatever it hit, subtract them together, stabilize it, and then times it by 800 to be the launch velocity. There was a massive bug, um, which is why this is here, stabilizing the character, if you don't want to know what happens, but I will show you. It is rather interesting. I can't jump off of that, sadly, but I will show you what happens if we go over here and we jump off the wall. It kind of bugs out and goes flying across the map. So without this stabilizing sign right here, everything kind of goes to shit. And then we've got the power damage and energy damage. That's the final things within the player's blueprints. So the power damage is get the world delta seconds, times it by the damage, which is just a input of a float, which gets called to in the laser. And if I was to add to this game and wanted to add more obstacles, it can also be damaged through those as well, be called to. So we want to get the world delta seconds and that damage, multiply it, and then subtract the power from that number and clamp it. What the clamp does is make sure that the value of whatever the damage happened doesn't go below 0 or above 100. Set that as the current power, change the ball material color with the value being the power, and then we want to set a condition of if the power is less than or equal to 0, which it should never go below 0 because of the clamp. If that's true, set the stats to dead, change the ball material color to 0 for the is on, disable the input, remove all widgets, create the death screen widget, add it to the viewport, and pause the game. And then for the energy damage, which is pulling the box, positive values equal damage, negative values equals healing. What that basically means, so we've got the damage, again, gets called to in the interactive block, not the elevator because it doesn't do any damage, to the energy. Get the world delta seconds and times that by 1. Times them all together and 1. And subtract it from the energy and clamp it again, just like we did here, and set that as the energy. The reason we've got this 1 here is because if the damage, like we did in the interactive block, the damage that we deal is minus 50. So if we're timesing this by minus 50, it's going to end up being minus 50. And then when it goes back to being nothing, it will times it by 1, which will then bring the energy back up. So that's everything within the player's blueprint, and all of it gets called to right here. Oh no, there we go. So I had that arse backwards. Here, when it multiplies by 50, it will damage, but here we've got the energy damage to be minus 25, so it's all permanently healing when it goes back up. So now let's go into the laser, which is a particle system, which again I found on the internet due to this being what we need on games engine stuff, not our own assets. We've got two different ones, which is electricity arc and P electricity arc. I don't know why they were named like that, but I used them both. One is within this, and you can see it like coming off the box here, and one is here to be the laser. And then what we do is more math. So on a tick, we want a line trace, get the actor's location being the start. So for example, right here, the actor's location is right in this line. And then we want to add that with the laser direction and trace max length. Multiply those together and add that to the actor's location to be the end. So we've set the trace max length to be 10,000 and the laser direction to be -1 on the x-axis. So it will infinitely go out this way until it hits something, namely being these rocks here. The reason I've got so many in a line is because if there was only one, it just didn't look right. It didn't look like it was flushing out the scene. That's the only reason there's 3 here. There's like 4 here. There's like 4 here as well. That's the only reason. And then we want to check if it has hit something. If it has, set the beam source point of the particle system here to be the actor's location, and set the target point to be the hit point. And the hit actor cast that to the player ball and power damage. So if what this bit here is, if it hits the player, it will damage the player. But if it's hitting the rock, it will set that as the new target point and not damage it at all. That was quite simple. And then we go on to the interactive block, which is a cube with the particle system inside of it and a massive detection trigger. The detection trigger is only this big because we want to be able to pull this all the way over here, pull this down into the pit, and pull this down from the ledge. It's the only reason it's that big. Then we go into the event graph. This one was quite large, didn't expect it to be. This just locks all rotations, but for some reason isn't working. Hopefully I can finish that in the final product. This initializes the cube. So on the begin play, we want to delay it because it allows all the other HUD actions to be performed. So creating the actual HUD at the beginning, so this right here. Then cast to the player ball, get the player pawn, set the player reference right here, which is a variable, and get from the player ball the HUD reference, because we've got HUD reference in the player. So we're getting the HUD reference from the player's blueprint and setting that as the UI HUD here. Lock all rotations, deactivate. Deactivating the beam. So what it's doing is when the player comes like over here, when the player comes into contact with the detection trigger, no, this right here is just deactivating it right at the beginning. Ignore me. This is what's the interaction text. This is deactivating the particle effect you can see here. So if we go in, you can see that when we go over to the box, it doesn't have that particle system on it until we press E. So then what we got to do is on component begin overlap this detection trigger. So as soon as it enters the detection trigger, cast it to the player being the other actor, get the controller, enable the input of E, and show the interaction text on the UI HUD. On end overlap, do the opposite, disable it. Then we go down here. So when we hold down the interaction key, which is E, it activates the particle beam. We did this using a gate on a tick event. So it's permanently checking if the player is pressing E. The beam being the particle effect, being the target. So if when it's pressed, activate. When it's released, deactivate. We also put a close interaction gate custom event, which gets called to later on. So the event tick being the enter the gate, so being the gate itself. The activate being opening the gate and deactivating closing the gate. And on the exit, we want to check if the player is valid, so is the player alive? And from there, if they're not valid, just get rid of the particle beam and hide the interaction text. That was for if the player dies in this pit while dragging the box down, it will completely stop dragging the box towards the player. However, if they are valid, then we want a sequence of things to happen. First off, we want to arc the lightning particle system to the player and take away energy while holding the interaction key. So first things first, we want to get the player reference and get the energy damage, like so. If we go back to the blueprints, we've got the player here, and we've got the energy damage down here. So it's calling to this custom event right here. And then we want to get the actor's location and return that as the beam's source point. And then set the beam's target point to be the mesh, so the cube. And that is what allows the player to have this lightning effect when dragging the cube towards them. And then from there, we've got the other thing that took a long time to figure out. And for some reason, it's another bug that I've got to iron out. But when the player runs out of energy within the thing, we want it to close the interaction gate and hide the interaction text. We tried multiple fixes to bring that interaction text back once it goes above a certain amount. Like one sec, we'll see it disappear once it goes to 0, but it doesn't come back until we leave the detection trigger and come back. I don't know how to fix that, and I spent a good part of a day trying to fix that, and even with peers, we couldn't figure it out. So we'll get there eventually, but we focused on finishing the project before moving on to bug fixes. So apart from that, we're comparing the float. So the float being the energy, comparing it with 0.5, because at that point, if the player won't be able to react in time. And then we got a tick to pull the cube to the ball. So we want to add force to the mesh. That force being the player reference actor location and the mesh world location subtracted, and split the vector, make a vector because we don't want to move it on the z-axis, and that return value being normalized and multiplied by the mass of the mesh times by 1,000, and that'll be the force. That's what allows us to drag it over. I think that's it on that, apart from in the cube itself, we also put the slide physics material, which is a inbuilt in-engine thing, which just allows the box to be slid around. Let's go to the elevator next. This was actually something I created. It was something in Blender, which was just a cylinder and a cube flattened. I didn't think it needed to be fancy to fit into this sort of aesthetic, and I just slapped this rock texture onto it, and it worked out like a charm. And then we put a detection trigger on top of that. And then within the event graph, again, there's a lot more than I thought there'd be. We want the HUD reference because, and with this one, it's a delay of 2. So in the interactive block, we've got a delay of 1. So there's a delay of 1 in the interactive block and a delay of 2 in the elevator. This is just so the system doesn't get confused and try to activate them all at once and then it'll bug out. But that would just be then the HUD reference. I don't know why I changed the name of them in every single different thing. It was really awkward, but there we go. So on component begin overlap with the trigger box, which is just this box on the elevator itself. We want to cast to the player, being the other actor, enable the input of E, and show interaction text on the UI HUD. Then on down, when you end the overlap, again do the same thing, but disable the input, hide the interaction text, and set is moving but not moving up. This allows so when you press E, which is the interact key, if the elevator is currently not moving, set it to move up, set it as moving, and then we've got the massive amount of math again. So on tick, we want to like each tick check if the elevator is moving. If it is moving, we want to check if it's moving up. If it is moving up, then we want to move the elevator by adding the speed of the platform to the z-axis until the up limit and setting it as the new location. So we've got the active location and we want to split the vector again into x, y, and z. Make a vector x and y, but on the z, we want to add the z axis with the speed of the platform, which we just set to 3. It could be higher, it can be lower, it depends on what you want really. Add those together and set it as the z, but also we want to make sure that if the z is greater than or equal to the up limit, being the condition of this branch here, set it to not moving and set it as the actor's location if it's false. So if this is false, So if the up limit is lower than the speed of the platform, then the new location is this right here. And if it isn't, if it is greater than, we want to set it as not moving and set it as the new location. This I forgot to comment. I'll do it right now. Sets the moves elevator down by adding speed of platform to the z-axis until down limit and setting it as the new location. So what it does is if it's not moving up, but the moving is true, then it means it's got to move down. So we got a branch checking if the actor's location is greater than or equal to the down limit, or less than or equal to the down limit. If that is true, set it as not moving and the actor's location to be the new vector. So it's basically the same thing that's happening here, but with subtractions instead of additions. And finally, because I'm probably boring you, it's the win state. So it's very simple. On component begin overlap the sphere capsule, cast to the player being the other actor, remove all the widgets, create the windscreen widget, add it to the viewport, and set the game paused. The reason I got it as a ball is like the player's actual ball is I run out of time for sourcing a actual win state model. My original idea was to find pieces of a cake and then have like 8 different levels, and then you're just creating the cake. But I didn't have time, maybe in the final product. And yeah, that's pretty much it. Thank you for listening.